Hi, thank you for joining me today. My name is Songtian Sonia Zhang, and I work at Princeton University with Professor Zahid Hassan. I'd like to talk a bit about the work that we've been doing recently, developing a field-free platform for Majorana modes in the superconductors lithium iron arsenide and lead titanium selenide. So this is an outline for the talk. I will first give a brief overview and motivation. I will then discuss how magnetic adatoms on topological superconductors can manifest as Majorana zero modes, and then present work on lithium iron arsenide and lead titanium selenide done using scanning tunneling microscopy, and finally, a brief summary and outlook. Most of this can also be found in this paper, so please check it out if you are interested in reading more about the details. So when we talk about Majorana zero modes, one of the applications that's often brought up is to use Majorana zero modes for topological quantum computation, and bulk superconductors would be a fairly ideal platform. So one approach, especially in scanning tunneling microscopy, is to search for zero bias peaks in field-generated vortices, which should in turn host Majorana zero modes. But external fields have several difficulties, including when we consider manipulation and braiding. So here the proposal is to develop a field-free platform by depositing magnetic impurities on topological superconductors. And here the two candidates that we're going to be studying are lead titanium selenide and lithium iron arsenide. There's a theoretical proposal that if we have topological surface states in a bulk S-wave superconductor with strong spin-orbit coupling and magnetic surface impurities, we can generate spontaneous quantum anomalous vortices which host Majorana zero modes. So this model was initially developed to explain zero bias peaks observed on an iron-based alloy superconductor, lead tellurium selenium, which exhibited all the properties of Majorana zero modes on these native excess iron impurities. Now, these Majorana zero modes on these quantum anomalous vortices are also expected to be sharper than ones found in vortex cores, and in this case, the role of the magnetic field is played by the spin-orbit exchange field. In this situation, the Majorana zero modes would start on one impurity and end on a spatially separated partner impurity. So recently, it's been found that iron-based superconductors generically host topological states, and in particular, lithium iron arsenide can be tuned through different topological phases by cobalt doping. It has a Tc of 17.5 Kelvin and a relatively high Hc2 of 15 Tesla, and this high Hc2 is useful for testing the Majorana zero mode hypothesis. However, through a systematic study, which you can also read about here, showed that there were no zero bias peaks at any concentration in the vortex cores. Looking at the superconducting structure, it has a fairly large gap of 6 MeV and is very spatially homogeneous. Post-deposition, we find that there are adatoms on the surface that are different from the native lithium iron arsenide impurities, which are dumbbell-shaped. Measuring in the vortex core on pristine lithium iron arsenide, we find in-gap states, but they occur at non-zero energy. Post-deposition, we observe a sharp zero bias peak directly on top of the iron adatom. This is also reproducible for several isolated iron adatoms, which is good because we want this reproducibility and not that it is only limited to a single impurity. So we now want to constrain it under different perturbations to rule out non-Majorana zero mode possibilities. The first thing we do is take a spatial line cut and find that it is tightly bound with a non-splitting spatial decay. Perturbing with a magnetic field is useful because it helps us rule out other potential in-gap states like YSR states or Kondo resonances. However, these are likely off zero or will split or shift with a magnetic field. And at 8 Tesla, the splitting for spin up and spin down states is expected to be about 1 MeV for G factor equals 2, which should be within our current energy resolution of less than 0.1 MeV. However, we can see that both for an in-plane 2T field as well as an out-of-plane 4T and 8T field, while the peak is suppressed, we see no splitting or shifting. And this is all behavior consistent with what we expect in a Majorana zero mode, which is extremely promising. So the second system that we study is non-centrosymmetric superconductor lead titanium selenide. And in lead titanium selenide, we can more directly probe the topology, which we couldn't do in lithium iron arsenide. So again, it's a non-central symmetric superconductor with a TC of 3.8 Kelvin. And both theory and ARPES showed that it has a Z2 topological invariant in the bulk, translating to spin helical surface states. And also previous STM studies found that there are in-gap states centered at zero energy, which again makes this a promising system to study. So because the topological properties are important, we first want to see if depositing magnetic adatoms destroys the topological surface states. We do this for a number of concentrations up to 2%, where the atomic nature of the adatom still holds, and each of the iron adatoms we can see sits interstitially between 3 surface lead atoms. So first we can see the QPI pattern on the pristine sample, so no iron deposition, shows the fingerprint of spin helical surface states, which is the 6-fold disconnected arc pattern that we can see here. Now we see that post-deposition, other than some broadening, this remains, meaning that it is robust to this deposition at least up to 2%. So having established that the spin helical surface states are robust to iron impurities, we turn our attention to the superconducting state, because previously here we were measuring at 4.2 Kelvin, which is above the critical temperature of 3.8 Kelvin. So first, let's look at the superconducting ground state in pristine lead tantalum selenide. We measure a spatially homogeneous gap over a clean area, and we do this with a superconducting tip, which gives us a higher resolution. And a superconducting tip will shift states at some energy epsilon by the tip gap energy delta T to delta T plus epsilon. Now, this will shift the coherence peaks in terms to some total gap of delta T is equal to plus delta T plus delta S, which in this case is 1.2 MeV, as we can see in the spectra here that we measure. And in this system, the sample gap is 0.5 MeV and the tip gap is 0.7 MeV. And this is further corroborated by previous measurements done with a normal tip, again in this work here, where they found that the sample gap size is 0.5 MeV. So now we want to look in the vortex cores, especially since, again, the zero bias states were previously observed. And what's really interesting now is that in the center of the vortex cores, there's also an in-gap state at delta T equals 0.7 MeV. This also further allows us to essentially calibrate the zero energy, as this is what we measure with a superconducting tip. So just to reiterate, in this sample, when we measure with a superconducting tip, the zero energy is at 0.7 MeV. So coming back to the deposition, we now do about 1% coverage and then measure the individual atoms. And immediately what we can see is that over a clean area, the superconducting gap is homogeneous, though there's a 1%, the 1% surface impurities introduces this shoulder state at zero energy. But most importantly, we see that directly on top of the iron impurity, we see these drawn in-gap states. And this in-gap state behavior is emphasized when we see the transfer of states from the coherence peak to this in-gap state when we do this subtraction. Again, looking at the perturbations, we find that there is a non-splitting spatial decay with a corresponding spectral weight transfer from the coherence peaks to the in-gap state. There's also no discernible splitting or dispersion, and it is again very tightly bound to the iron adatom. We find again that every isolated iron adatom examined exhibits an in-gap state at this energy, again of delta T or epsilon equals 0 MeV. To visualize it more directly, we deconvolute the superconducting tip from the measured spectrum, and we see that both the vortex core and the iron adatom shows a zero bias peak, and that the one in this on the interstitial iron impurity is much sharper than the one on the vortex core. So what we have here is that we measure a zero bias peak that's repeatable on many of these isolated iron adatoms, and it is consistent with all expected Majorana zero mode properties. So in summary, we have essentially found a field-free platform for Majorana zero modes by controlled deposition of magnetic adatoms onto topological superconductors, lead tantalum selenide and lithium iron arsenide. And these observed zero bias peaks exhibit all the properties of Majorana zero modes. A clear future direction is to manipulate and braid them, which is a necessary step for topological quantum computation. I'd like to acknowledge all our collaborators, especially Jiaxing, who works with me very closely on all of our STM experiments, and Professor Hassan, who is my advisor, as well as all the theorists who assisted us and helped us develop this theory, and of course the sample growers, without which we would not have any samples to measure. So thank you for your attention. Feel free to message me with any questions, and again, any extra information or any details can probably be found in the paper here, which I highly encourage you to read. Again, thank you for your attention.